So, ladies and gentlemen, this is our 100th Zoom presentation. So,
well done.
Well done to everybody involved. Cheers.
Cheers.
Well done.
Thank you.
Tonight's speaker is a long-time member. That's all I'm going to say about him. And I'm going to hand over to Steve Taylor. Over to you, Steve.
Thank you very much. Evening, everybody. Everybody well? Good. You've all gone quiet. What a change. Anyway, as you well know, Andy Devey. A short biography. Bearing in mind he wrote it. So Andy is a fifth-generation coal miner, or at least he was, from Wakefield, West Yorkshire. Educated as a mining surveyor and a chartered mining engineer, and was a colliery manager in Doncaster and Scotland in the late 1990s. He became interested in astronomy from an early age due to having a bedroom with no roof. And later, no roof, what a joke. And later started with binocular observing until he got his first serious telescope in 2004. He became a member of the Experimental International Society in 2006, and everything went downhill from there. A visit to his late cousin, Christina Rosanna Devey, an MSc astrophysicist at Keele University in 2002, permitted his first observation of the sun in hydrogen alpha light, and from then on, he was totally hooked. He bought a BST in January 2005, and where the weather was permitted, he's made daily solar observations as part of the BAA Solar Observing Programme. He started imaging in 2009 and made the front cover of the BAA yearbook in 2011 and had articles published in Astronomy Now and the BAA Journal, together with about 40 articles in various electronic magazines. He's been the first guest in the Let's Talk Astronomy video series in 2011, and shortly before he moved to Spain. He's proficient in outreach activities in English and Spanish, and had his first article in Spanish published in November 2013, and recently has just had his first book accepted for publication in English and Spanish. He has posted hundreds of solar activity animations on space weather and achieved their front page. He's also gained permission from the head of the Global Oscillation Networking Group program to use their data from 7 separate sites to make movies of solar activity and to house them on the solarexplorer.net website that is run since 2010. So can please everybody put their hands together and give a warm welcome to Andy Devey. Thank you.
Thank you, everybody. I do hope you can hear me okay. This is my second talk, so that's 2% of them I've done, Paul. So I am definitely doing my bit. So just bear with us a second while I share my screen. You'll notice my laptop's all in Spanish. Right. Just check it, Paul. Can you see that okay?
That's lovely. The largest sunspot in over 30 years.
Yeah, and I'm going to be speaking about active region. That's what the AR stands for. And its designated number was 2192. This sunspot occurred in October 2014, which I will show later. And when we get a sunspot, they take just over 2 weeks to travel across the face of the solar disk that we can observe from Earth. I'm just going to give you a little bit of history about sunspots, because sunspots were the first solar phenomena to be observed by amateurs, and lots of people think of the first sunspot as being by Galileo Galilei. Now, he was the first to publish about sunspots, but a British astronomer called Thomas Harriot actually discovered them and made the first drawing. And this is a page from his notebook back in the 8th of December in the year 1610. Now, according to Alan Chapman, who is our honorary president, I believe still, Thomas Harriot, one of his cousins or one of his family members was actually implicated in the gunpowder plot of 1605. And that's the reason why he didn't publish anything, because he preferred to keep his head down before he lost it, which was one of the problems at that time. But his sunspot drawings predate Galileo's by quite a number of months. And as you can see on screen, you've got positions, the dates. I'm not going to try and read it all, because I can safely say his writing is nearly as bad as mine. Now, I mentioned Galileo Galilei. Is that animation running okay, Paul?
It's fine.
Yeah. He was more meticulous at recording his drawings, and quite a number of them have since been animated. Obviously, that wasn't done at the time, but this is one of the series of drawings animated from nearly 2 years after Harriot in 1612. Just to explain a little bit about the solar cycle, our sun's a G2 type star, so it's a yellow star. It is a variable star, but the variability isn't very high. But it does have a 11-year solar cycle. Now, after 11 years, the polarity flips from north to south. So the actual full solar cycle before you return is around about 22 years. But during the solar cycle, you get periods of intense activity. These are called solar maximums. Okay, and you get in between the solar minimums when there is very little activity. And as Mick will tell you, same as myself, these are times of very little activity, not a lot to see unless you like to spend a lot of time on the smaller scale structures. And if you like the big dynamic events, such as myself, it can be a little bit boring. So I've just had a 3-4 year, not a full layoff because I've been doing daily drawings, but my astronomical activity has been much reduced, and hence 2 more books written. They were in publication, but they were actually published last year in August, so they are now out in print. The first recorded solar cycle was from February 1755 until June 1766. As you can see there, the average solar cycle is 11.3 years, and the cycles were discovered by Johann Rudolf Wolf, and he actually published about the solar cycles in 1852. A little later, I'll refer to my website, and one of the pages, or 3 of the pages on there, are an online library where a lot of these monumental publications, you can actually read them electronically and flick from page to page, such as Kepler's work, Galileo's work, Schwab's work, Wolf's work, even some of Einstein's stuff on relativity. So anyway, I'll come to that a little bit later. So sunspots, if they're big enough, you can actually see them by the naked eye. And I've personally seen them without any protective equipment during periods of intense fog or early in the morning, but I would not recommend that to anybody. I've heard of some people that like to look at the sun as it rises, and why? You're going to destroy your eyes. So I will always make the safety notice that any type of solar observing, you need to take ultimate care, because you've only got one chance, and that's with each eye. So no safety shortcuts. Always look on the internet, or like with experts such as myself and Mick and one or two others in the society that can give you tips to keep you safe. Now, some of these sunspots, when I say naked eye, lots of people often use things like welding masks or glasses for eclipses. And if the sunspots are big enough, with those eclipse glasses or welding masks, you can actually physically see the sunspots. This area here dates back to April 1947. So you're talking almost 2 years after the Second World War finished. And it's the largest sunspot cycle, sunspot recorded over the last 410 or so years of solar observations. Now, sunspots themselves are extreme areas of intense magnetic activity. And where you see the black areas, these here, these are called the umbra part of the sunspots. And the magnetic field lines are coming out vertically in these areas. The areas to the side of them, the grayer areas, these are called the penumbra, and the magnetic field lines there are on an angle. And within the penumbra, we have what's called fibrils, and some of the animations that I've done, you can actually see the plasma running along these fibrils back in. Now, the general surface of the sun is round about 5,500 degrees centigrade. Where you have sunspots, the temperature is about 3,800 degrees. So they are not cold areas, they are relatively cooler, so they appear darker. So it's just basically a relative thing on light intensity. So just to give you an idea of scale of that particular sunspot, here you can see the planet Jupiter. So these are seriously big features, and the way we measure them is in millionths of the visible hemisphere of the sun. So this particular one, sorry, just bear with us a second. I believe that particular one was about 4,800 millionths of the solar hemisphere. So 4,800 is roughly 0.5% of the total area of that hemisphere. So, as I said, I'm going to be talking about the largest cycle in the last 30 years. So the question is, what was the one just prior to it? And that one was AR 6368, which occurred in 1990, and it attained its peak size on the 18th of November that year. And this figure here it was 3,080 millionths of the solar area. Now, it wasn't the most active. Shortly after, some 7 or 8 months later, there was another cycle, which was also in this, another sunspot in this solar cycle 22. And in the interval from the 1st to the 17th, it released 5 X12 class solar flares and an X10 class. Now, solar flares are measured A, B, C class. The C's are relatively small. Obviously, A and B are even smaller. Once you get to an M class flare, these are the medium class. The extreme class are the X class flares. But within the X class flare division, anything above X10 is classed as a super flare. Now, the largest flare that's ever been measured using current instrumentation actually drowned out the sensors at an X28. And it's believed from modeling that that potentially was an X48 class flare. Now, that actually occurred in 2004, but really, really lucky for ourselves, it was on the sun's western limb, which is actually the right-hand side of the sun just before it rotated away. So the blast shot out and hit Venus. It didn't affect Earth. That would have had some severe consequences. Now, prior to that, the first solar flare was seen and recorded by a guy called Richard Carrington back in 1st of September 1859. And fortunately, there was a second observer whose name I can't remember at this moment. So because 2 observers had seen the same event, it was classed as a genuine feature. Now, about a day after that, the telegraph system across most of the world, you know, the initial communication system, it became so highly charged that they had to disconnect the batteries from it, and it still ran on the energy from the sun. Now, that particular one caused auroras down to the equator. So it's believed that it actually bent the Earth's protective magnetosphere into the soil. So you can imagine what effect that would have had on our current mobile phone technology and electronic cars and things like that. So that's why there is now a science stream called, discipline called space weather, which is able to give alerts for things like that, predictions and some sort of early warning. Okay. It's been mentioned that I actually live down here, quite close to Almeria, and we've lived near a small town, which is an old mining town called Bedar, since October 2013. So within 2 months of moving here, I'd got my observatory built, and so since then I've had a stable observing platform. Okay, so this is the observatory that I use. It's basically a 2.4 meter cube, and it runs, can you see these steel rails here? It's very heavy because within the wood inside, there's all steel rebar every 6 inch, so there's like a tiger cage inside it, but you cannot see it because of an internal wooden lining. But by taking this floor plate out here, the close position is at these stops. So this is where the shed is normally. I undo these turnbuckles, which are the same as on a boxing ring, take the floor out, and then I push the whole observatory back, and I can be observed in an imaging within about 3 minutes from putting the key into the door. I'm sat at a little table here because if it's a nice day, I like to sit out, and this is a little micro observatory with a black screen there, so I can see what I'm doing when I throw it over my head. And I've got a little cooling fan here that runs from a battery from a solar panel charge. Now, this is a steel column that I put into the floor that's full of concrete. Initially I had a EQ6 on there, but that's since been replaced by a much larger, heavier capacity EQ8. And what I have, my main instrument is a TOA 130, same as we have at the observatory, which is, but instead of it being in parallel to a C14, I have 2 solar telescopes either side. Now, this one here, that's actually fitted with a Herschel wedge. So by the little box there is my imaging camera, and I can put it into either white light, hydrogen alpha, or calcium K. Now, the other thing I want to point out is on the floor, I have placed yellow chip-ins. Now, because they're bright, they're highly reflective, and the other thing is, because they're small, they don't act as a heat sink. So this actually helps me to keep the air reasonably cool within the first 2 meters, so that I'm not getting a lot of atmospheric disturbance immediately from the ground. It does help seeing to some extent. Now, fortunately, the rails run in a north-south direction, and I'm lucky that from on the house here, I can see the sun from sunrise over the sea to within 2 degrees of sunset over the nearest mountain ridge. So for a solar observer like myself, it's ideal. This is my little mate Alfie, but sadly I lost him in 2018. So looking out in our garden, we have lots of natural grasses. These are called Esperto Grasses. And what's really interesting about these grasses is 2 things. One, they act as a thermal body, so the grass absorbs the heat rather than the floor getting hot. But 2, they were actually responsible for educating Victorian Britain. Now, the reason for that is the area where we live, in Victorian times, from about 1870s, they used to export 30,000 tonne a year of this from the local ports, from Carboneras to the south of us, through Garucha and as far as Cartagena to the north of us. And it all went into Tilbury docks, where it was made into pulp for all the newspapers in Britain. So that's just a little throwaway fact for you, that one. So the reason I've got a power pack battery pack on, in the first few years, we got a lot of annoying short power cuts. Even in nice weather, you get a 30-second power cut. Now, if you're doing an imaging run, you don't want to be pestered with that. So what I used to do was run it from the power pack and maintain the power pack charge. But fortunately, over the last few years, the electricity supply stabilized, sorry. So I mainly run from mains electricity. You can just see, oh, this square box here is a DMK imaging camera. Now, this particular solar telescope here is a Coronado SM90 calcium K telescope. I believe there are only 10 of them ever built, and they were released for sale back in 2009. And the one I've got is actually #1. So it's quite a collector's item, that one. The one behind it is a 90mm hydrogen alpha telescope, and I've got an extra Etalon at front. So it's actually, because one of the Etalons were a double stack unit, I'm actually triple stacked, which means that the bandwidth that I'm imaging in is less than 0.4 of an angstrom. And an angstrom is a billionth of a meter. So this is the setup. Just bear with me, I keep losing my arrow because what we've got there is like a tilt screw, so you can tune the Etalon onto the hydrogen alpha waveband. Now, the reason for all the tin foil is just to reflect the heat away from the mount. The mount is a good tracking mount, but I've also got a guide camera as well, so I can stay on good tracking accuracy either side of 1 second of arc. Now, this is a guide camera tracking mount system. I've also got a laser pointer, so if I can't be bothered going through star alignment, I'll go onto a known object, and particularly if I'm planetary imaging, using the laser pointer, and I'm in an imaging. Now, this is the important part here, because this was delivered in 2015, and it's the MSAS Southern Observatory sign. Thanks for that, Les. Okay, so I'll start to talk, or move on to talk about AR 2195, sorry, 96, and 92, AR 2192. And the first indication that I got that something was approaching, possibly big, but until it actually rotates and faces you, you don't know. And this is a still from the UDIPAR India Hydrogen Alpha Telescope on it's what's called the Global Oscillation Network Group, or GONG website. This is open source, but in 2012, I had the idea to see if I would be able to use their source to actually animate solar features and put them on my website. So I had the idea, I sent an email to Gong, and actually got a response from the head of the American Solar Observation Program for the whole thing. A fellow called Frank Hill thanking me, thought it was a brilliant idea, and of all the 30 scientists that it got working for him, none of them had that idea, so I was really pleased with that. But that's another story. So looking at this, when we see features, although it's opposite to our compasses, this is classed as the eastern solar limb. And can you see they look like a curved structure there? Well, these are what's called post-flare loops, and they are areas of magnetic field lines where the plasma starts running back to the surface. And they're indications that quite a large solar flare has occurred, and this is the magnetic reconnection after that flare explosion. So I saw this. This was at 07:49 universal time, and all the imaging that I do is all date stamped with universal time. So all my images, and I rotate them correctly, so they are a genuine scientific record rather than a pretty picture. Even if it's brilliant, if it's not given that scientific context, it spoils it. So if you do observing, get the context, put the time in. So I thought I'll go out and have a look. Now there were unfortunately sporadic clouding, but as you can see, I were a bit later, 9:19. So I only got some 7 minutes of imaging, but because it's going lighter, I've had to try and compensate for the cloud. But hopefully, is it running okay, that ball?
It is.
Yeah. Can you see the plasma running down?
Well, I can.
Yeah. So, and at the other side, which is fainter, the plasma doesn't do that as a loop. It actually runs down both sides at the same time. And the reason for that is these magnetic field lines protrude into the chromosphere, which is this area here. Now, what I've done is I've actually overexposed the surface. That's why the surface is pure white. So these faint features are actually picked out. Now, just going back to the gong image, all these images that you see on gong are actually a combination of two images. There's an overexposed disc in the background, and then the disc in the foreground is placed on top of it automatically, and you can see the cut line all the way around. Now, the other thing with gong is when you get dark areas such as sunspots, they tend to automatically puts a white patch over it, which you'll see a little bit later. So that's telling me that there's something coming, but with no idea what yet. So the following day, 16th October, this was a few days earlier, but it's the same area. So this is even further behind. You get prominences, they're quite faint. These are like gas clouds that are suspended. You can see a few here. Now, the other features that we get are filaments, which are the same thing, but you actually see them in front of the solar disk. Now, this is a 12th panel mosaic from the 16th of October. And when I stitch these together, the actual image is about 1.2 meters in diameter, and it holds its resolution. But obviously, when I shrink them down, you can't see that. But when you get a limb flare, they are much brighter. Can you see how bright that object is compared to these prominences? So what I thought, well, I'll get a full disc and then we'll have a go at animating it. So this is, can you see that's actually an M4.3 class, and it's a limb flare. So when I animate, the individual images are made usually from a stack of about 300 video frames. And originally I used to use a program called Registacks to process. Nowadays I use one called AutoStackit, and then I put the finished result into Registacks for its wavelet. And the program, you're effectively compensating for atmospheric dispersion. Obviously, the better the atmospheric scene is, the better image quality you're going to get, no matter what the program is. And the more video frames you can get, say if you shoot 1,000, you pick your best 200. And also, the shorter the time of imaging. So if you can image at, say, 1/200th of a second, you will get a better quality image than 1/10th of a second, because it's actually freezing the effects of atmospheric dispersion. So again, this is just a precursor that something's coming, but we don't know what. So I had, yeah, sorry, I did get it right. The first one was the 15th. Now, unfortunately, November and October, we do get odd days with clouds. So this particular sunspot had rotated around, and it actually gave out an X1 class solar flare. But if you look at the time from 04 in the morning to 06, 6:30, this occurred during hours of darkness for me. So what I've done is I've used the gong data from Learmonth in Australia, and I've made an animation using their data of that solar flare, which is this bright area here. Now, just to explain what a solar flare is, these sunspots, the magnetic fields that get twisted, imagine an elastic band, but when that actually breaks, the magnetic energies convert into thermal energy. So the area, general area that you see here is around about 6,000 Celsius, but the solar flares can be 1-2 million degrees. So now this particular one, it's not a CME, coronal mass ejection, but it does fire out a promise. Can you see it in that direction? But the sun's gravity was sufficient to pull it back, so it wasn't a high energy vertical blast, that one. Now, other things that you can get associated with solar flares, and I didn't see any of them from this particular sunspot. You can get shock waves that run out, called Moreton waves, that can radiate outwards. So they're a nice feature to image. And I've only imaged 2 of those so far during my imaging career. So this is the 19th. Now, this is an animation. This is my data. So it's only a 11-minute animation, this, and for me to show the dynamics of these fibrils running into the umbra, I like to do an hour at least. Now, when you look at it, the imaging, you can see, hopefully you can see, times when it's really sharp and then times when it goes off a little bit. Now, that's nothing to do with processing. It's due to the atmospheric seeing during the image run for that particular image. And when I'm imaging, depending on the dynamic activity of the feature that I am imaging, I will either image between 1-minute intervals, 2 minutes, or as much as 5-minute intervals. And the longest imaging session I've done are actually 7.5 hours at 5-minute intervals on the prominence, and I had to stick at it. But Judy kept bringing food down for me, and with 5 minutes you've time to run up to the toilet and back without missing anything. So, but you can see this was with a solar wedge. Oh, sorry, just drop back a second. So quite high resolution that, and you can see what's called a light bridge running across the middle, and all the little sunspots. They're all associated with this one huge active region. So that was on the 19th of October. So the next time I had an imaging session was on the 21st of October. And what I've done here, these are all 4-panel mosaics. So if I want to do a quick action, to do a 12-panel excuse me, a 12 panel mosaic, I'm usually imaging for about 5 minutes, as I always start this point. You image that bit, then this next bit, making sure you've got overlaps, then this next bit, then I come down on that line and then back on that line and then finish on that line. But with a 4 panel mosaic, instead of grabbing two, it's a third of the images, so it's a lot quicker. So what you're seeing here, and I've scaled them, are the white light with the large sunspot area here. This is the calcium K, which is in the lower chromosphere, and these white features here are the large chromospheric network features. Now, both white light and calcium K, you can see the convection cells, or granulation as it's called. The granulation here is just a little bit lower than on the photosphere. The hydrogen alpha is even higher in the chromosphere, and you see a much a much different structure. Now, as you can see, the sunspot, if you're on band, is not as prominent in hydrogen alpha as it is in white light, and calcium K. Now, solar flares are very bright in hydrogen alpha. You can see them in calcium K, but it's very rare to see them in white light. I've never seen a white light flare or captured one so far. What I'm just showing you here, just showing you the individual images, just to get so you can see a little bit more resolution. But they are orientated, and as you can see, the universal time and dates there, so it is a true scientific record. And when I image, I'm same as Mick Nichols. Our better images, we send them to the BAA journal, and we both had images published in the BAA journal as first part of the solar observing program, which has been going for well over 150 years. So what I've done there is that's just a crop of the other picture. So within that, you can see well, unfortunately, when I did a test report, it's a lot crisper on my screen than what I'm able to deliver to you over Zoom. But you can see all the fibrils, all the structures within the convection cells in the granulation, and all the different umbral areas and all these grey penumbral areas. So this particular sunspot had the length of 16 Earths. So this is from there to there was 16 times the diameter of the Earth, and bigger than planet Jupiter. I believe Jupiter's 11 times the diameter of the Earth. So Jupiter is about that big as I'm going around my cursor. Okay, so this is the calcium K image, and you can see just how big this sunspot is compared to relatively normal spots that we get. Again, that's from 21st of October at 10:02 Universal Time. And this is 9:50 Universal Time. And this is the hydrogen alpha. Not as impressive in hydrogen alpha, but as you'll see later, hydrogen alpha does have other benefits. Okay, so by the 22nd of October, it was shaping up to be the biggest sunspot in many years at that time. its area was approaching that of AR 4, so that should be a 6, sorry, 6486. Okay, from the last one from the previous cycle, which was cycle 23, and that covered 2,610 millionths of the solar disk, and that occurred on October 30th, 2003. Now, there was another big one from that particular cycle. That's it, from 2001. This is the relative size of the sunspot from 1947. And this is our target here, which is AR 2192 from 2014. So very, very big. So from space weather, 23rd of October, since that week had begun, the giant sunspot had produced 27 C-class solar flares, 9 M-class solar flares, and 2 X-class solar flares. The most powerful of which was an X 1.6, and that occurred on October the 22nd. And I captured it. So that's the solar flare. The sequence, it runs from 1430 to 1548 universal time, so about an hour and a quarter. Now, it's flickering a little bit, and that's just annoying thin cloud. And even with all your endeavors within Photoshop to try and smooth it, it's still difficult to completely eliminate it. It's just a feature of the atmosphere. But what I've done then is I've smoothed it a little bit more, and this is me zooming in on the flare. So it's the same image, but I've just cropped it, so I've been able to enlarge it. So you can see the area, when it builds up the area, it really goes probably for a distance of about 9 Earth diameters. And that was a X 1.6 class flare. Okay, so 23rd of October, I caught an M1.1 flare, and that's early in the morning from 9:46 to 10:11 universal time, so 25 minutes. You can see it doesn't extend as far. There's just a little bit of a shock wave along there, and you can see a bit of a plasma rejection that falls back. Medium class flare, not massive. Okay, going to the 24th of October, you can see how it's traveled a significant way, more than halfway across the solar disk by this time. It's still actually growing at this stage. Now, what I've done, this is the color that I always image in black and white, but this is the color if you look with your eyes and you're still young enough to be able to see calcium K, because it's just on the limit of our vision, but younger people can see it a lot brighter than us oldies. But you can see just how big the features become. What I've done there is same image. I've just cropped it so you can see the detail. You can see all this grainy structure. They are all the convection cells, and the granulation. You've got the light bridges. You've got the penumbra with the filaments, fibrils, sorry, and the umbra. And then this next one, I've actually caught a couple of subflares there. This sequence runs from 9:59 to 10:90, so it's only a 20-minute sequence. If you look there, you see a couple of subflares there. These are probably B-class flares, and there's another one there. Very, very, I keep losing my cursor. A very tiny one in this region as well, and along that light bridge. So that's they are calcium K K flares. Okay, same day, this one at 9:30. Here I've gone on to a 12 panel mosaic. You can see nice high resolution. Again, this is another one of my 1.2 meter diameter images. There's a filament there that's probably about 400,000 miles long. So that filament is longer than the Earth to the Moon distance. Possibly there to there is Earth to Moon. Now, same day, this is a bit earlier from 8:04 to 8:34. So that's a 30-minute sequence. I actually caught an M4 class flare. You see the brightening in this area? Now, flares, think of them as growing pains, because every time a flare goes off, it's these sunspot areas are losing the magnetic activity, and it's through solar flares that they gradually decay. So unfortunately, same day, and look of the draw. Can you see this is running from 20 universal time? So this is running after sunset for me, but this was a Sod's Law, an X3.1 class flare, and this was the largest flare that this particular sunspot banged off. Now, the gong have automatically made these penumbral areas white, and I've had each one in Photoshop trying to paint them in black before I animated it. So that's why it looks a little bit odd, but at least you can see, and this particular flare has gone, and you can see the loop activity all the way across it's covered the whole active region from one end to the other. So that's 16 times or possibly 20 times the length of the Earth, that solar flare, a huge event. And then on the 25th of October, this is from about 1600. I can't see numbers going too quick, to 1920 universal time, and this was an X1 class flare. So at least you're seeing the X class flares that this particular active region gave off. But if you look at that one, this area here, I haven't coloured the penumbral area in, so that's as it comes. Sorry, the umbral area. That's as it comes straight off the gong site. Now, I was out the following day, which was the 26th of October 2014, and I caught an X2.2 class flare. And can you see the end of it here? So I got it about 15 minutes past its peak. So it's just the look of the draw. Pardon, 33 minutes past its peak. But you can see again, it's absolutely an enormous area. Now, that's just a still of it, just at the high point. So you can see the flare, it runs right into the light bridge above the umbra, and way out past, can you remember where them little grey penumbral areas were? It goes right across the whole active region. Okay, so 27th of October, and this is me quoting from Space Weather. This giant sunspot was crackling with flares, and at that time it had become the biggest in nearly 25 years, and it was still growing. At that time it actually covered 2,750 millionths of the solar disk, and it's an area equivalent to more than 16 planet Earths if you skin them all and spread them out flat. Now, since the active reading appeared on 19th, it had at that stage unleashed 5 X-class flares and a dozen M-class flares. Now, most intense of those, they had caused HF radio blackouts and other communication disturbances on the day side of the Earth. And I don't know if, maybe in questions, if Phil, I believe, does a lot of Lax's radio astronomy, if he had any disturbance from it. So that 27th, you can see the sun's now getting close to the western limb for the sun. It's east by our compass, but western limb for the sun. And that day I was happy. I got an M6.7, thinking that will be it. But now stayed persistent, and a little bit later, I caught an X2 class flare. Now, what I've shown you here is a still, because this is my little observing box. Can you remember that fan on the side? And this is my battery here. This is what I'm seeing on my computer screen. But because I'm imaging through a wedge and, sorry, a diagonal, the images, I have to flip them horizontally to get the correct orientation, and that which I do in Photoshop. But that's what I actually see. And if you look, you can see my ugly mug image reflection on the screen. Now, at the end of this slideshow, I'll show you the video I made. It's only 45 seconds long, recording what I'm seeing in the telescopes at that time. So I'll do that in a little bit. So later, this was from 1421 to 1536 universal time, I actually caught this, another X2 class flare. So I didn't do bad. I caught 3 out of the 6, which isn't a bad hit rate really for a fella from Yorkshire in Spain. Okay. October 28th, it's now getting very close to the western limb. Some subflaring, or this was a C5.2 event. A little bit of sporadic cloudy cover, but you can see I'm still monitoring activity there. And then the following day, this was on the 29th of October, you can see it's about to leave the western limb, and that long filament still there, and as you can see, that's not far off touching the western limb. This is another one of those 12 panel mosaics that I do. And then what I did, I took the opportunity to, the seeing were quite poor on that one, but you can see all the little flare activity once they get onto the limb. You see little spicules jumping up and down, lots of little sub-flares on it. It was a seething hive of activity. That particular flare there were actually M1.4 class flare within that. So I believe it's that one, the when it runs along there, that's the M class. So during the 2 weeks, it had been the biggest in nearly 25 years. Well, bear in mind that's over 7 years ago. We're now at, it's in the last 32 years. As it rotated across the disk, it produced 26 M class flares and 6 X class flares. Now, what's most astonishing of all, 0 Earth-directed CMEs. So we didn't get any massive auroral activity from it. Now, this is the logarithmic scale from the NOAA government.gov website, and this line here is the X-class flare line. So anything above X1, X1.6, X3.1, X1, X2, X2. So they are the X-class flares. This line here is the M-class flare line. So as you can see, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm not going to count them all. And then the C-class flare line is that one. And if you look during its activity, all the time, it was above the C-class flare line. So it was virtually, it was continuously above the C-class flare line with this sunspot. So next solar cycle, we're actually in cycle 25 at the moment. The prediction is for a solar maximum. These last two solar cycles, that were 23 and 24, they had what's called a double peak. So instead of it coming to one peak, it had effectively two solar maximums. And that was the prediction, which I believe was predicted in 2019. Obviously, we're in 2022 at the moment. So this is up to the end of last year, and the actual mean activity is in front of prediction at the moment. That's all we can say. Doesn't mean to say it will stay there, but it's always a case of watch and see, because the predictions can be notoriously inaccurate, even with all the instrumentation and modern solar physics. There's still a lot to be explained about solar activity. So I put this one on because this activity area here is a big region that's actually emerging now. Now, I can't see none of this at the minute because of horrible weather. We've had a huge lump of cloud and also an enormous, I think we've got half the Sahara Desert, and that's just on mine and Trevor's gardens. There's so much at the moment. But if any of you have got a solar telescope or are proficient at using solar filters such as Barda filter, have a go at imaging this at the moment. It's looking like it's one of the biggest, if not the biggest, of this the new solar cycle number 25. Okay, I've mentioned my website. That's it. Unfortunately, we're having problems with it. Glenn and Sean have had a go at it, but we keep getting hit. I used to have a contact me link that got attacked by this, some sort of Chinese casino bloody virus thing. So I was getting, I think at the worst, 300 emails an hour from it. And that even having spam filters on it. But there's another virus on it at the moment. And the problem with the site is it's on an old Joomla version, which was originally built in 2010. And we just need a time slot and available time to get it onto the newer version of Joomla. And it's that that's causing problems. So there's all sorts of rubbish coming over at the moment. And then that's it for that one. So I've got just two more little things for you. So I'm going to stop the share at the moment. I've tried where I can to show my images here. So I'm just going to go full screen. Can you see that okay?
Yep, it's coming through.
Right, there's going to be a little bit of sound with it, and I think it's just interference, but this is me sat at my chair in my observatory. That's my laptop within my little observing box, and this is what I saw. So you can see the atmospheric shimmer. This is done. Can you see that, Paul? Okay.
It's coming through really
Right,
well.
okay. So this is done with the data from the Solar Dynamic Observatory, which has 10 different sets of instruments aboard. Now, for some reason, the animator has this is flipped 100. It's rotated clockwise by 190 degrees. So what you're seeing on the top right should be bottom left and rotating the other way. But I'll just let you enjoy, and you can see the delights that our sun offers to us keen amateurs. So you just saw plasma rejection firing out, and another one. So ejections are lots of post-flare loops. That was a solar flare that shot off. Now, what you'll see is, unfortunately, the way the instruments are set up, when you get the extreme flares, it does tend to drown the chips out a little bit. So our amateur work is useful, interrogating what's actually going off within the flare. So we are still relevant. So the Sunspot now is just coming on to, you can see there's a lot of plasma being flung out. When we get to the first X-class flare, I'll tell you. It runs for about 5 minutes, this video. Is it enjoyable, Paul? Because I can always...
I'm just thinking, what sort of time period are we looking at? Is this over a week?
No, this is 2 weeks of activity.
Right, okay.
So you've had about 4 days there. You see the X-class flare there? So lots of post-flare loops on that limb there from a different active region. That was an X-class flare. That was the X1 class flare, that one. If you look at, you can see on the instrumentation, the camera is starting to pan to the left now. So we'll start to lose the eastern limb shortly.
Which spacecraft is monitoring this? Is this taken from, Andy?
Solar Dynamic Observatory.
Right, okay.
I think it's a L1 gravitational point. I think I worked out it cost 4 million times my PST.
Well, your PST is not at the L1 point.
No, it's not, no. See, this area here is firing a lot out, isn't it?
Yeah.
It's all part of the same structure. Yeah, well, for us solar astronomers, and Mick will probably tell you the same, when we get a big active region, this is these are the things that we really dream about. What I found when this active, that were an X-class flare went off then, when this active region were at its peak, or for the times it weren't cloudy, I was in the observatory for the night. Let's see, that's the X 3.1 flare, that one, for 9 hours, sometimes 10 hours, and then our image processing. So I was pulling 18-hour shifts. So anytime now, that's an X2. And then it gives an M6 off, and then another X2. Yeah, that's the other X2 plus flare, that one. About another minute or so, and it'll start to leave the western limb. But if you compare this activity with the general activity, it's chalk and cheese, isn't it?
It certainly is. I was just looking at the shade range from the dark to the light, and that's not a linear range either, is it?
No, no.
There's an element of logarithm.
Yeah.
Logarithmic.
Yeah. Nearly done. I'll just let it run onto the limb, and then now this sunspot, it left the limb on the 29th of October 2014, and 14 days later it rotated back round. So I had the intention of doing an image run as it crossed for the second 2-week period. But unfortunately, my dad was seriously ill, and he actually died on the 14th of November, the day that it rotated back into view. So that was that, because I was back at UK for that event. So I'll stop that. So hopefully that were okay. I've done.
Okay, so let's go back to gallery view so we can see all the usual suspects. Andy, as always, a pleasure listening to you, and some amazing images, and I'm talking about yours, not the professionals. And you did a good job in animating the professional stuff as well. It's nice to see. I'm sure we've got some questions.
Yeah, just bear with us a second, Paul. I'm just closing a couple of things down. So
okay, I'll just remind.
Right.
I'll just remind Roy if he can sort of channel the questions coming from the club room. We're looking for digital hands. Your oppo there.
We'll start with Mick.
Yeah, we'll start with Mick. Mick Nichols. Welcome, Mick Nichols. Cheers.
I have a couple of clarification on things, Andy. You mentioned about Wolf discovering the solar cycle. I thought it was Heinrich Schwabe that discovered it.
It was.
But you mentioned Wolf.
Oh, I got it wrong.
Oh, right. The second thing is as well, you mentioned the 1947 Sunspot group having an active region number.
Yeah.
That again, active regions.
No, it weren't. It was me that put the AR on it. They got some other prefix in front of it at that time, haven't they?
Yeah,
Yeah, you're
Wilson,
right.
I believe. Mount Wilson, I believe.
Yeah, it were through Mount Wilson Observatory. Yeah, definitely. You're right.
Well done, Mick. Got to keep him on the straight and narrow. Trevor.
Fascinating, Andy, as always. Just three little questions. I was wondering about any radio emissions from these X-class flares and whether we can pick up with our seldom used SDR radios, these software-defined radios. So,
Well,
any radio emissions?
You should be able to, but I'm not a radio astronomer. To be honest with you, Trevor, it's not something I've looked into. I believe Phil may be able to answer that. But yeah, you can definitely pick flares up with radio, definitely. They give quite a radio signal.
I was wondering whether they give any early warning as they come over the limb edge.
Again, possibly. I always use the visual assets to me. There's actually a solar flare alert system, which I believe Mick subscribes to. I don't. I tend to do it all visually on a daily basis. First thing I do when I get up, I check the space weather nomographs and gong as well, and it's like a fishing. You can have an active region, but you don't know when it's going to bang off. It's only when it actually does bang off that you get the radio signal or the light signal 8 and a bit minutes later.
Got you. Okay, then the other one was I know you can get like strange weather patterns on the Earth, like at a solar minimum. And I was wondering whether some of these largest sunspots, whether we've ever detected weird one-off events weather-wise.
Yeah,
it must have some effect.
Well, the one that I mentioned to you about the one that Carrington saw in 1859, they were getting a phenomenon even in Caribbean called St. Elmo's fire, running down ships' rigging.
Oh yeah.
So and then the other main atmospheric phenomenon is the aurora, and occasionally I've personally seen auroras, and it was from the March 1989 one that it took half the power grid in Quebec in Canada, didn't it? That one, it blew up 3 of the main transformers.
Okay, yeah. Last quickie then, I know that CMEs obviously you're losing material from the sun, but I wonder whether any of these X classes allow material to escape, or whether it's all pulled back in.
It all depend on the trajectory of the blast. Sometimes, and I've seen flares, even low M class, one were a 1.6 class, and when it ejected material, it came straight out. It was really odd, and the implosion, a lot of it fell back. There was a significant CME as well, but the whole thing was as big as the sun when it fell back in, and you can get some really odd effects. It all depends on the direction of the fracture of the magnetic field, I believe.
Yeah, I think I saw one that looked like a something being ejected, but when it hit, it almost, I don't know whether it was almost fake news. It seemed to splash on the surface.
That particular one, it was almost as if the sun had been hit by a bullet from other side, and it were like an exit wound. Yeah, that's the one, isn't it?
It is. It seemed to, like you say, as if a bullet had hit it, and you got that shock wave as it came back down the material. Yeah. I just thought it looked too good to be believed, that. But anyway.
No, it was. Yeah.
Thanks very much, Andy. Great presentation.
Cheers, Trevor.
I'll this one.
Okay, John Leach.
Hi there, Andy. That was remarkable, mate. I couldn't keep, I just glued to the screen. Beautiful. One question, Andy. When you do mosaics, I know that the process. But do you do them manually, or do you have an automation so you work out the exact areas?
Manually,
Really?
and
Wow.
it takes me an eternity. Yeah, the
Right.
biggest one I tackled, John, was a mosaic of the moon, 81 panel.
Right. Wow.
They just to let you know, it took me 3 hours to image and 30 hours to stitch it all together.
I
And
can appreciate it. Yeah, yeah.
I had to build a panel in Photoshop that was 3 meters by 3 meters.
Wow.
Yeah, and the finish.
This up, and I thought surely somebody must have done a program to automate.
There is, and Mick uses it, and I believe Tony does as well. It's called ICE or something like that.
Yeah,
But-
Microsoft
Okay.
Ice.
Right.
Yeah, but I like to line them up myself. I just enjoy doing it because I used to like jigsaws when I were a kid.
I can see that. I'm with you on that, Andy. Many thanks again, Andy.
Okay, thank you, John. And Tony Morris.
Hi, Andy.
Hey up, Tony.
I know you like jigsaws, Andy, but there's no corners on the sun.
New start.
But there's a good edge, there's a lot of edge pieces to it with.
Andy, excellent imaging, excellent, really good. I was interested in the one that you'd done on the 24th of October, the M class.
Yeah.
So when the flare material was coming out of the sun, it looked darker. So when the material's coming up the magnetic field line, I presume it's losing energy, therefore temperature.
It is, yeah, and it almost fires like a filament out. And I've had quite a number of them where filaments are shot out and then they get pulled back in. Yeah, and it's like a vertical launch filament and then back in. Yeah.
Yeah, but it seemed to be darker though.
It is, yeah. It is, yeah. Yeah.
Right. Okay.
Yeah. Yeah.
So one of the other things, Andy, on some of your other animations, when the flare material came out and it went up the magnetic line, do they always follow the exact same path back, or do the lines twist? Because some of them don't appear to have enough energy to get over the
Yeah.
peak of it.
Yeah. So what a flare is, Tony, them lines are twisting and actually fracturing and reconnecting.
Right.
And when you get a big reconnection, that's when you get all, it looks like one of them slinky springs, can you remember, or half
Yeah.
of it. And that's the magnetic field lines rebalancing, I believe.
Right. Okay.
Okay. I'm going to bring the club room in. So if you can unmute yourself, Roy. Right. And, hi. Any questions from downtown Swinton?
Yeah, just to answer some of the questions that Trevor raised earlier. Yeah, when we get some of these solar flares, it can affect the magnetopause and it can shove it and alter it. Apart from causing the aurora, it also interacts with the stratosphere, and around the polar region, it can alter it where it affects the jet stream. And some of these big freak weather events we've had over the past 20 years have been linked to some of these solar cycles, some solar events. So they know now it does actually affect the weather via the magnetopause, stratosphere, troposphere, right down to where we are. And especially because we're in that zone, we're either just under it or just above it. So we do get other swings. What was the other question? There was another question he asked as well. Trevor.
Hi, Phil. Yeah, it was maybe making use of the SDR radio to pick up any spurious radio noise coming from these X-Class or any others.
We're just trying to download the SDR radio onto a new laptop, and it's something I'm going to have a go at this summer. But I need a different aerial to listen to the song. So when Mick's in clouded Sheffield, we'll be able to tell him when there's a flare going on. I need a different aerial, but yeah, we should be able to show it into the sun and how it interacts with the ionosphere as well.
Any information you've got on that, Phil, would be great if we
Yeah.
could
I
get
think
copied
it's
in.
something we might be working on this year as well.
Okay.
Okay. I think Mexborough and Swinton Astronomical Society is some secret group of wind-up merchants. Mick Nichols.
Oh, yes.
Yeah, that actual group. It's funny Phil mentions about Claudia Sheffield. I actually got 2 images of that group for the entire 14 days from the UK. And all those flares it kicked off, I got none. But this new spot group, what you've mentioned to Andy,
Yeah,
I actually got, and the one below it as well, that little one below it,
yeah.
3 C-class flares in one day yesterday. So for me, that's a record.
Okay,
Well,
so
At least as a team we're getting them, Mick, aren't we?
blue skies over the next few days.
Imaged more flares than what I've seen, Andy.
Sorry, Mick, I missed that.
You've probably imaged more flares than what I've seen.
Yeah.
Okay, I'm going to bring Bill in from Cleethorpes. Bill, welcome.
Hello, yes, great talk. I enjoyed that. Just, you mentioned that there were no CMEs. Was that surprising? Because there was obviously a lot of activity going on.
Yes, very surprising. Normally, with something as big as that, and especially when you get 6 X-class flares, you'd expect CMEs involved with it, definitely. Yeah, it was very surprising.
Have there been any explanations for that from the academics and so on?
Not that I've seen.
No.
Not that I've seen.
Okay, thank you.
Go on, Mick.
Just if you not know any reason for it, Andy, I watched a talk by Lynn Smith a couple of weeks ago, and she actually said that most of the flares on the sun actually occur 2 years after maximum. Is there a reason for that? Because she didn't see no reason either.
Now, if Lynn don't know, that probably it's not been proved why yet.
Right.
It's something I've never seen before, but like that particular one, it were a double peak, and it was the second peak, weren't it, for for the cycle 24 when that big sunspot went off.
Yeah.
But what's interesting though, Mick, I imaged one of them in 2017. I can't remember the date, but it's on my website. One day an X 9.3 flare went off, which was largest at cycle. So I missed it and I was fed up. So I went out and imaged, and X8 went off on limb. So I got the flare and all loops from it. So, but like you said, that's a couple of years after the peak.
Okay, Mick.
Yep, sound.
Ladies and gentlemen, I think that just remains for us to give Andy Devey, our operator and owner of the Mexborough and Swinton Southern European Observatory, a huge welcome.
Which is open for visitors, remember?
It is open for visitors. A huge welcome for rounding off our 100th Zoom talk. Andy, thank you very much.